Okay, let's start the class. And today we will be finished the lecture 2 about aerobic respiration. Briefly mention the anaerobic respiration. Then we are going to hopefully can open in the genetics section. This is what we talk about is aerobic respiration. And we said the overall picture, which is glucose, will be going through glycolysis, which is a branch, and will generate pyruvate. And the pyruvate will be going through a circle. This is a circle which is called a citric acid cycle. And I said very important, we would love to see how many ATP generate. So how many total ATPs generate will be our job to do the calculation. And in the lab section, I will be break down again today if you join lab 2, lab 3, lab 4 to make you refresh it. But in the lecture, we're not going to repeat it since we already did from the beginning to here, which is 2 ATPs if in the absence of oxygen, which means it is coupled with fermentation. Now when we talk about the fermentation here, obviously is a homofermentation, which is pyruvate become lactic acid. And the 8 ATPs if presence of oxygen, now which means there will be part of aerobic respiration. So today we're going to be focused on very important is this TCA cycle. So we're going to draw on the blackboard on the right side. And we want to talk about the detail of that. This is the picture right there. You can read it, but I still want to draw on the blackboard. First of all, okay, this number for the citric acid cycle, there is several names you should know. We could call it a citric acid. Because there's a major component, is citric acid, citrate, always calls. It also could call TCA cycle. What this means? Tricarboxylic acid cycle. Because most of these are COOH. You will see a lot, carboxylic acids. There's another name is Krebs cycle. What does that name come from? This has come from a British scientist from University of Sheffield, which is Hans Krebs. Hans Krebs, 1900 to 1981, 81 years old, and in 1937, he is verified the citric acid cycle. So, in 1953, this is a Nobel Prize of physiology, and medicine area. So it's a breakthrough in the modern biochemistry area, which is we talk about aerobic respiration. So there are the 3 names. That's where it comes from. So sometimes citric acid cycle, TCA cycle, Krebs cycle. Okay, so what it is? This is all comes from the pyruvates. Start from here. So first of all, there is a so-called transition step, which is pyruvate. And you need to know the pyruvate structure so far. COOH, CO, it's a ketone, then becomes CH3. Pyruvate will be going through so-called transition step. It's going to lose carbon dioxide And then it will be also coupled with NAD, reduced to NADH2. So remember, this H2 there, add into NAD, you're adding electron there. The proton at this moment is equals the function as electron, so NADH is generated. Then have another thing gonna come in, is SCOA, coenzyme A, right there. This is a very long chain of the chemistry components. And we don't talk about that. Organic chemistry, they talk about this a long name. This is just an acronym, just to let you know. So what's going to happen? Then become COOH, CO, and SCOA. The name called acetyl-CoA. Okay, so everything starts from here. This is a transition step. We call it a transition step. And we also call here, when you take out of the carbon dioxide, decarbonation. Okay, because CO2 comes out. So everything starts here. Is acetyl-CoA is this structure. Then they go through the cycle. So here we're going to draw it. Is COOH goes here, CO and SCOA. This is acetyl-CoA. Then we go through the cycle. Now, very important, since it's called the citric acid cycle, so when you learn the structure, you need to know what is citric acid. Okay, that's number one. If you don't know the citric acid, like you don't know the glucose structure during the glycolysis, it makes your life more difficult. So you need to know what is citric acid. Okay, so we go here. Citric acid. What is citric acid? COOH, CH2, COH, COOH, and then we go here, CH2, and COOH. This is citric acid. And also, we sometimes call it a citrate. So if you look at our textbook, we can just double check. Our textbook right here, they call citrate. It's the same thing, okay? This is citric acid. Now, here is something we want to mention. In your textbook or in your biochemistry class, the next step goes here. You have another thing happen, which is lose water. So, become what type of the chemical? COOH, CH2, COOH, CH, and COOH. This one is called cis-aconitate. In your textbook, biochemistry, you talk about that. However, in the microbiology class, our textbook, we skip that because this is barely found in the bacteria if you use E. coli as a model. So this one, we usually here do not talk about this too often. Okay, so we will directly go to the next step. Is isomerization, basically. So that's why we do COH, CH2, COOH, goes here H, here C, OH, H, then COOH. This is isocitric acid. Now, in your textbook, it also said when you go here, possibly goes here, which is you add water back. When you add water back, you look at the double bonds here. Of course, the OH is not go back, because OH is already here. So they switch. That's why this H is here, OH goes here. Okay, if you really, that's in your biochemistry textbook. So we don't, the isocitric acid, we just go right here. So you can see the isocitric acid is right here. So that's why they skip one here. Okay, this is nothing happened. Kind of, you can understand it's isomerization. Now they go here. There is something will be happening. At this moment, they will lose CO2, decoordination, and at the same time, we have NAD reduced to NADH2. So become a chemical. That chemical is very important. So COOH, CH2, CH2, COOH. This is alpha ketoglutarate. What is a keto? This guy right here. This one is very important. This is the one, if you know other things connected to lipids oxidation, connected to protein synthesis, there is a lot of the chemical could go from there. So this is, we call it a metabolic precursor. Okay, that's important chemical. Now, every time when you see something this happens, I usually will suggest you to circle it, because NAD reduced to NADH2, that means something gonna happen. Okay, alpha ketoglutarate. These type of things is easy to lose, because you know your feeling about it. This is kind of like the electron negativity. This type of structure here is not easy when you have an O in the middle. So what's going to happen? COH, CH2, CH2, CO, and then SCOA comes out. This SCOA is readily existing in the cell wall structure, cell membrane system, to ready for use. You have to have a storage these things. This is called succinyl-CoA. Okay. Then what's going to happen? The same thing. Decarbonate, NAD, also reduced to NADH2. So everything happens here, you're going to do it. Then this one usually it's a little bit flat, right here. SCOA, they have to do something. Okay, COOH, CH2, CH2, COOH, succinate. And at this moment, this S-coenzyme A has some function. They will trigger something energy generated, which is GDP, add phosphates, become GTP. Now, obviously, this is different from NAD reduced to NADH2. So this is another level of substrate level phosphorylation. And I mentioned about that, not only ATP, GDP, CTP, even UTP, they all could be an energy currency as a backup. So succinyl-CoA, when you see something in the middle, that's easier to lose. So we go here. COOH, CH, CH, COOH. Fumarate. Now, once you lose the oxygen, where are they going to go? FAD going to be reduced to FADH. Thiophene, adenine, dinucleotides. This something happens again. Okay, so we're going to circle it. When you have a fumarate there, have a double bonds right in the middle. That's not stable. We have to add something back. So what happened? COOH, CH, we're going to add water back. So CH2 and COOH. This is malate. Malate, we're simply going to add the water back. So we're going to add the water. Okay, once the water comes out, this is not stable. You see the hydroxy bonds right there? It's easier to be loose. So it will be loose again, actually. So what we're going to lose again? Become COH, CO, CH2, and COOH. This is oxaloacetate. and then you go back to this guy. And actually, it's not go back to this guy. This should be combined together, then they do it. Okay? Now here, when you lose the water again, you lose the water, you lose H2, so NAD have to be reduced to NADH2 again. So at here, we're going to circle it. So this is a citric acid cycle, basically like that. So we're going to do the calculation. The calculation here, what we're using, make your life a little bit easy, is NAD reduced to NADH2. We were thinking about, this is 3 ATPs comes out. In new biochemistry class, the new addition will say this is 2.5 ATPs because the consideration oxygen phosphate ratio. That's okay if you want to use to calculate like that. And FAD reduced to FADH2, we say it's generate 2 ATPs. In your textbook, it is 1.5 ATPs in biochemistry class. Also, consideration oxygen phosphate ratio. So we can do a calculation here. How many? I usually we're using another marker to do a right. 3 ATP right here. Then we have 3 ATPs right here. Then we have 2 ATPs right here. Then we have 3 ATPs right here. And do not forget the transition step right here. We also have 3 ATPs because it's included. And also don't forget, there is a one substrate level phosphorylation, GTP comes out, and that equals ATP. So how many ATPs generate here? Is 3 ATPs multiplied by 1, 2, 3, and 4, multiplied by 4. This is all comes out NAD reduced to NADH2, so that is 12 ATPs. Okay, then you have 2 ATPs, which is coming from FAD reduced to FADH2. And I should use this arrow like this, And then don't forget, one substrate level phosphorylation, 1 ATP. So you add up them together is 15 ATPs. Now do not forget, when you come here, the pyruvate could do a 1 cycle right here. Another pyruvate could do 1 cycle right here. So how many of the total? There's 2 cycles. So that's why it's 15 ATPs multiplied by 2 equals 30 ATPs. And originally, we already talked about through glycolysis, in the presence of oxygen, there is 8 ATPs come out. So what is the total? So the total we can write here is 8 ATPs adding 30 ATPs equals 38 ATPs. Now this 8 ATP is coming from glycolysis. Now of course this is glycolysis in the presence of oxygen, so it's involved the electron transport chain. And this 30 ATPs comes out at PCA cycle. Now you're gonna tell me, you're gonna say, it's a little bit different from we learned in the biochemistry class. We get 36, how come you get 38? Remember, in the biochemistry class, what you talk about is eukaryotes. Animal plants are more universal. This is the bacteria. Okay? This is the focus on the prokaryotes is bacteria. So for fungi and yeast, which means yeast and the modes, what are going to be the ATP, total ATP? It's very similar. In your class, it's the same number. It's 38 divided minus by 2 equals 36 ATPs. Why? This is 2 ATPs. You have to passing the mitochondrial matrix membrane system. So I usually say this 2 ATPs is a ticket. Is a ticket of cost of the ticket of methylchondrine mixer gate. Okay, this gate is just a nickname. Okay, like you go to see a museum or you go to see a theater or cinema, go to see a movie, you need a ticket. That's $2. 2 ATPs is for the ticket. So for fungi, it is 36 ATPs. So this is basically the calculation for the citric acid cycle. Now, in order to help you for the exam 3 to get a good grade, what we're going to do is that I will be increase the extra points a little bit. If you write a name there, the chemical name will give you 0.5 points. If you write a chemical structure, will give you 1.0 points. That will be 1 point. Okay? So one chemical structure and one chemical name equals together is 1.5 points. That will make your life is much easier. Some of you here is working Dr. Kim Barnes or Dr. Cassandra Lam is in a biochemistry program. You already taken the classes. It will be certainly a benefit for you. And some of you sophomore or senior already taking biochemistry classes and you do the refresh. But I don't want to put you some stress on you. At least, depends on you how you got in the exam 1, exam 2, depends on your energy. At least you should know the chemical name there. Is that right? That's a bunch of points. And the chemical structure, not for everything, for some of you, especially if you're a sophomore, but you try your best to write some. Let's say citric acid, you at least you know. Glucose, you at least you know. And some of them, you know about that. Okay, that will be certainly help you. Then another thing we want to talk about later on when we go the DNA translation, we will talk about is a side chain of the amino acid. That is certainly also going to be lots of points help you to increase your overall grade. Okay, so that's what we have here, and then I also will take a picture here, and then will be put on the eCampus if some of you could review them later on. I'll put the camera there. The review, and then help you to study. Okay, so that's a TCA cycle. So let's go back to see the slides again. Something you have to understand. So I have these slides, and I also have a Zoom recording. So I'm also going to upload it into the eCampus, and you can take a look. We talk about aerobic respiration, use glycolysis TCA, and relate to the electron transport chain and produce ATP. So this is Epstein-Meyerhof pathway. When we mentioned the glycolysis, what we talk about here is basically Epstein-Meyerhof pathway. There are 6 carbons, 3 carbon, and this is the one which is in the textbook what we talk about. We already mentioned. So how many ATPs generate? This means in the absence of oxygen, coupled with fermentation, there is a 2 ATP hydrolyzed used here, 4 generated here, through substrate level phosphorylation. So 2 ATPs. But when we think about aerobic respiration, this is you have to think about, because it's related to the electron transport chain, and theory behind that is chemosmosis. So remember the summary of glycolysis, you have 2 ATP. This is an individual cycle which is coupled with fermentation. So then we talk about oxidative phosphorylation, which is electron transport chain, ATP synthesis. It's a hollow enzyme, and associated with respiration. This is electron transport chain. And this is electron transport chain, and continue for that. If in the eukaryotes, it's on the mitochondrial membrane system. In the bacterial cell, it's in the cell membrane system. This is chemosmosis. Peter Mitchell mentioned about this. And this is the overall picture, how they generate the proton motive force. So we want to mention here is that the proton motive force, not only bacteria has, not only hetero organisms has, photosynthetic bacteria also can do, which is coming from the light, going through photosynthesis, generate proton-motive force. Then all these things are the same to happen. Then we move on to the aerobic respiration. This is a transition step. So pyruvic acids will become coenzyme attached with the coenzyme A, which has become a cyto coenzyme. Then this is basically the TCA cycle. So you can see it's a two molecules of carbon dioxide, 3 molecules of NADH, 1 FADH, and 1 GTP. Now most of the textbooks, they also separate that. They say this is 6 carbon. This is 6 carbon. Then you go to alpha ketoglutarate, this is 5 carbon, and then later on becomes all 4 carbon. So that's all the biochemistry stuff. So we don't mention really detail here. But here is something we also want to mention. All these, you see these blue color, pyruvate acetyl-CoA, oxaloacetate, and alpha ketoglutarate. These we call it a metabolic precursor, because they are not only stopped there, they are involved in multiple biochemistry metabolic cycle. And you see, if you see the overall picture, it's more complicated than this. So these are the chemicals we call a metabolic precursor. And this is basically is a calculation. Just want to let you know, the left side here, which is using the new calculation, which is 2.5 ATPs for NAD become NADH2, and 1.5 ATPs for FAD reduced to FADH2. And what I have here is the older one. This is 38 ATPs. But be careful, this is for bacteria. Okay? So you can mark this is a new calculation, which is what I did here. And this one is the older this is new calculation, and this is the older calculation. And you can do both in the exam, but you have to using only one standards. You can be this one, you use 2.5, another one you use 3. It's like confusing people. Okay, so this is a older one, use 3 ATP, and this is a new one, use 2.5 ATPs. So we already mentioned about that. Okay, next what we want to mention is aerobic respiration. We will say this very briefly. Anaerobic respiration, we mentioned about is electron transport chain. Electron donor is organic chemical. And the electron acceptor is inorganic chemical, but the inorganic chemical is not oxygen, which means other than oxygen. So when you list it here, you can see it could be ferride, sulfide, carbon dioxide, nitrate, there's so many, and even fumarate. And because of the distance between the beginning of the electron donor to the electron acceptor, the voltage difference is not as large as aerobic respiration. So, generally speaking, anaerobic respiration is generated over ATP is less than aerobic respiration. How much it is? It is somewhere between 2 to 36. I would say that. This is a picture. It's really nice, the table, and you should mark here. This is give you the conclusion of chemoorganoheterotrophs. Basically, is a bacteria we talk about. Through aerobic respiration, anaerobic respiration, and fermentation, how many ATP they generate. This will give you a very good conclusion. So from here you can see the aerobic respiration have glycolysis and the TCA cycle. The terminal electron acceptor is oxygen. So substrate level phosphorylation, how many they generate? The ATP going through substrate level phosphorylation theoretically is 4. If you remember, there is a 2 generated through glycolysis, 2 in the TCA cycle is actually right here. This is 1 ATP, is 1 GTP. GTP is same as ATP, and 2 cycles. So there is a 4 ATP generated through substrate level phosphorylation. Since the overall ATP is 38, so how many ATPs through oxidative phosphorylation? 34. Now anaerobic respiration. Anaerobic respiration, you need to know. Basically, right here is very similar. They have so-called revised or remodeled TCA cycle, but this is included. So, substrate level phosphorylation, they also generate is 4 total. However, their oxidative phosphorylation is different, is variable. So therefore, their overall ATP generated is 36 or less. I will say the good number will be 2 to 36 between that. Fermentation, we already mentioned. The only pathway is glycolysis, and they are coupled. And we mentioned fermentation. The electron donor is organic chemical, electron acceptor is also organic chemical. And the ATP generated only substrate level phosphorylation, only 2. And no oxidative phosphorylation generated. So here is something we want to mention. Through the fermentation, you see there's only 2 ATPs generated. Through the TCA cycle, there is so many ATP generated. However, you said that, when I said that NAD or electron carriers, they must be recycled. Which means it's better you're going to have these type of things, which is NAD. Have a well, is that right? Have some empty places you could add the proton to make them saturated. But why here you didn't see it? Look at here, it's all saturated. But why the bacteria still can survive? The reason is there is so many precursor metabolic generators. They can easily to be going through another metabolic pathway. Another one is there is a much more ATP generated compared to 2 ATPs. So for the fermentation, you only have 2 ATPs generated. It's 2 less. So I want to combat the 2 less ATP generated. So how are we going to do it? So we have to recycle this. This is something like you have a lot of money. All the money generated, you can put it in a lock drawer or some places, just holding there. This is you only have $2, you have to use it, so you have empty wallet every day carry on to bring the money. Is that right? That's the same thing. So for the fermentation, the bacteria going through that process, they always should have a recycled NAD. If not, they will not be survived. But for TCA cycle, it's okay because there's so many ATP generated and there is so many chemicals is a metabolic precursor. That certainly helps a lot. Okay, so this is a conclusion table, and I think it is very important for the chemoorganol heterotrophs. This one, every year I go through a little bit simple. This is pentose phosphates. We don't talk about this too much. That's in your biochemistry class, another class to talk about. Basically, all these cycles are the same. You know the structure, you know the chemicals. But we only talk about several conclusions. What is the pentose phosphates going to generate? Pentose phosphates usually right here. Okay, something goes here, then right here. Pentose phosphates, there is a several conclusion right here. Very important. Their precursor material is for 5 carbon. That is used for biosynthesis, DNA and RNA. So they give the raw material to generate DNA and RNA. Their reducing power is not NADH, it's not FADH2, it's NADPH. And they will generate precursor metabolites. So the major thing here is 3. They have a raw 5 carbon sugar ready for biosynthesis, DNA and RNA. They generate reducing power is NADPH, is not NADH, and actually pentose phosphate pathway is kind of right in the middle between catabolism and anabolism, but the majority of the function is anabolism because the other precursor metabolites could be there and then become DNA and RNA. Okay, so pentose phosphates we usually don't test you in here. You have other classes talk about that. We just let you know the conclusion about this. But the completed aerobic respiration is important. Okay, so that's why we usually start from here. So overall here, this section actually is important for the exam. We have a lot of questions from these slides. The key thing what you need to know is the fermentation, aerobic respiration, and don't forget the story behind the substrate level phosphorylation and oxidative phosphorylation. So when you draw this cycle here, when you see NAD reduced to NADH2, you should ask yourself, this is oxidative phosphorylation. What is that? It's connected to chemosmosis. What is this? Okay, and then this is substrate level phosphorylation. What is that? We talk about delta G, remember? These things is important, the thing here, and also the whole calculation and the chemical thing. Okay, so that's the thing we talk about, is exam 3, lecture 2. And the detail of these we also will be mentioned again in the lab, and we will be help you to revise it, and the video will be uploaded and also going to put a picture there. So let you help you as much as I can to understanding these material. Okay. Okay, we finished this part. Briefly for biochemistry, we'll jump into another big topic, which is genetics. Will not be too complicated, but some of the basic information I do want to mention in this class to help you understand. First of all, our outline for the genetics section will be central dogma. Okay, what is central dogma? Everybody should be familiar with, or you at least heard about, which means the DNA going through a replication process. And not only for that, when they have a replication, they'll become RNA, and this is called transcription. And then the RNA later on will become a protein. This is called translation. Now, we never forget about, in the old central dogma, they didn't mention one thing, is the RNA could go back, become a DNA. This is called a reverse transcription. Rely on the enzyme reverse transcriptase. So this is the overall story. Therefore, our overall outline of this section, we will be mentioned basically as the DNA, RNA, the structure, we talk about that. So we will focus detail replication, the detailed transcription, especially at the beginning, the enzyme, the RNA polymerase, it's important, and the translation. Okay, these will be the outline. We are going to be doing these one by one. So today, we're not going to get to detail of the replication yet. We're going to go over several of the old history. Talk about the DNA. So today's important thing will be DNA history. Or we talk about all these very typical experiments. This is today's job. Okay, first thing first. When people start to learn genetics information, DNA, RNA, this is not really all of a sudden, or everybody said we're going to start to do genetics. Well, people becoming so smart, or no, not really. This is back to 1912 to 1915, actually beyond that. By the time that's another big pandemic in the world is Spanish flu. So when the Spanish flu comes out, it took about 6 years. Even today you still have a flu. It's a mutation from the Spanish flu, to be honest. So all I know, pretty much like a coronavirus. You're going to be there for hundreds of years. It's just a mutation by the mutation. This is what the Spanish flu comes out. At the time, people want to find a vaccine. That's the key. And therefore, people do lots of the animal studies, lots of the bacterial media studies, talk about the molecular stuff, but all the final destination is their objective, they want to develop vaccine. That's why they do so many studies. There are so many studies. When they develop the vaccine, when they get to the bottom of the genetic information, at that time, they want to solve the problem is transformative principles. So which means which chemical is really transferring genetic information? There will be the question. Chemical used for transfer genetic information. This is the key. They want to find it. That's why there is so many important study comes out. So the first one, what we want to talk is 9028 F. Griffiths. A very important study, a very nice and a very genius British scientist. He did a study which is Streptococcus pneumoniae in mice. So you should already be very familiar with Streptococcus pneumoniae, will cause pneumococcal pneumonia. We mentioned that this is gram-positive. Coccell, it's diprococcel, have ammonia generate. Is that right? Remember, when we talk about this pathogen, what it looks like. There is a heavy capsule. It's a polysaccharide surrounded, will let the bacteria become very virulent, which means people can die. Because of this structure, there is two different types of the Streptococcus pneumoniae. What are the two different types? One of them is smooth Streptococcus pneumoniae. Now, why it is smooth? Because it has a capsule. Once you have a capsule, you're feeling it's like a shining, looks like. That's why it is smooth. Then at the same time, F. Griffiths find another chemical which is a rough one. Another Streptococcus pneumoniae is rough one. It's not shining. Okay? The rough one, because there is no heavy capsule, so it is non-virulent. At the first one, we usually say it's a virulent, which means people are going to die. So the rough one, we also say it's a surrogate. So he did some interesting study. What he did? The first step, he injected a smooth Streptococcus pneumoniae, go to a mice. The mice is dead. Then we can say this is a positive control. Then he injected a rough, non-virulent surrogate Streptococcus pneumoniae, go to a mice. What happened? A mice is alive, a mice is survived. Okay, what are we going to do? This is, you can say, positive, negative control. I have this smooth Streptococcus pneumoniae. I'm going to heat treat it. Okay, so I heat it. I heat treat it. Or we say heat injure. Then I'm going to inoculate to a mice. Inject it to a mice. What happened? The mice is alive. Okay, that's good, which means the toxication is gone. Okay, let's do another study. I have a smooth one. Okay, heat injure. Then, in the same solution, I'm going to add a rough one. I combine them. And then the whole thing, I'm going to inject another mice. a big mice. What happened? The mice is dead. What this tells us? There is something happened right here, is that right? They definitely have some toxication material, you can say, or genetic information is transferred from the heat-injured smooth Streptococcus pneumoniae go to a rough one. What is this one called? Right now we know it's called transformation. So what tells us? Something is a genetic stuff there, a genetic chemical. But we don't know what it is. Is it a DNA? No. Is it an RNA? We don't know yet. Or maybe it's a protein just. We don't know about these things, what it is. Something will be there. And this connection, this transmission, we call it a transformation. Okay? Then Griffiths did this all the time. Spending a lot of times to do. He's gonna go ahead to focus on it. Then hundreds, thousands of the mice were sacrificed and died during the research. He made some progress. This is 1928. In the 1930s to 1940, all the research did in his lab, millions of, not millions, thousands of mice have died. Because he focused on the study. He gave some progress in 1941. However, he was died because of the German bombing during the Second World War. And his lab is completely destroyed. He's died in the lab, just the bombing. Okay? So, a very young, intelligent scientist is died. Then, looks like the work is stopped. However, people record it. Okay? This is a very